Hello everyone, my name is Seungmin Hong and I'm with Gwangju Institute of Science and Technology. The title of my talk today is AC NEGF simulation of nanosheet MOSFETs. Introduction. The non-equilibrium Green's function NEGF formalism is a standard simulation method for quantum transport. It has been actively applied to the simulation of nanoscale transistors. Nowadays, various NEGF tools, either academic or commercial, are available. For example, the usage map of a certain NEGF tool found in nanohub.org is shown here. We can find that the NEGF simulation is performed by many researchers worldwide. However, in most cases, the NEGF technique has been applied only to the DC steady-state simulation. It is difficult to find transient and AC small signal simulation result for semiconductor devices. Of course, we may find some works in the physics journals, but those works are seldom related with the conventional electron devices. Unfortunately, recent theoretical advances have not been applied to the electron devices. It is in strong contrast to the conventional TCAD tools. As we all know, the TCAD tools are fully capable of DC, transient, and AC simulation. These days, even the deterministic Boltzmann transport equation solvers can support transient and AC simulation. We need to improve this situation. The maximum limit of the intrinsic RF performance can be investigated by the AC NEGF simulation. One possible application is simulation of terahertz devices. For example, there is a theory that the plasma instability in the two-dimensional electron gas can yield a voltage oscillation at terahertz frequencies. We hope that the AC NEGF simulation provides a way to verify this theory. In this work, I want to present our implementation of the AC NEGF code. It has been applied to the nanosheet transistors. Some important relations in the AC NEGF formalism are introduced. Detailed derivation procedure can be found in the references. Since the AC NEGF simulation is based upon a solution of the DC NEGF simulation, notations for the DC NEGF simulation are shown. The retarded Green function GR satisfies the following equation. The lesser Green function is calculated from the retarded Green function and the lesser self-energy. Once the lesser Green function is obtained, from its imaginary part, the electron density can be calculated. In this slide, the grid structure is explained. Since the decoupled mode space approach is adopted in this work, the cross-section in the YG plane should be uniform along the x direction. A three-dimensional tensor grid is assumed for simplicity. However, it is noted that unstructured grids in the YG plane can be used without much difficulties. Assume that the DC NEGF solution is available. Also, the ballistic transport is understood. An AC voltage excitation is applied to a contact. The amplitude is V amp and the angular frequency is omega. The retarded Green function is written as a sum of the DC retarded Green function and AC one. Here, the AC retarded Green function GR sub AC is given by this equation. Let me introduce some notes about this equation. First, the first term in the right hand side is GR at E plus half omega. It is not GR at E. Also, AC potential energy V sub AC appears. Of course, V sub AC is determined by the Poisson equation. Finally, the AC retarded self-energy is related with the DC retarded self-energy. Now, we consider the AC Lagrange function. It is given by this equation. It is lengthy, but three terms in the right-hand side can be easily understood when we remember the DC Lagrange function. Again, the AC lesser self-energy is related with DC lesser self-energy. From the AC Lagrange function, the AC response of the electron density can be easily obtained. Of course, the AC electron density is used in the AC Poisson equation. The AC NEGF solver has been implemented in our in-house device simulator G device. It was previously applied to the terahertz simulation and the transient BT simulation. It has its own grammar for the input command file. For example, an input command file for the DC NEGF simulation is shown. Here, we define a set of coupled equations named DC low underscore NEGF. As the first example, the AC responses at 0 Hz are calculated and compared with the quasi-static result. A silicon nanosheet transistor with 5 nm by 10 nm cross-section, 1 nm oxide thickness, and 7 nm channel length is simulated. The total length along the x direction is 25 nm. The source drain regions are 9 nm long, and the doping density is 10 to the 20 per cubic centimeter. The channel region is intrinsic. The gate contact is 7 nm long, and the gate work function is 4.3 electron volt. Effective mass Hamiltonian is employed to describe 6 elliptical valleys in the silicon conduction band. 001 surface and 100 channel are assumed. VDD is set to be 0.5 volt, and semi-infinite relays are used for the source-drain contacts. Before the AC NEGF simulation, we have to perform the DC NEGF simulation. The convergence criterion is the potential error smaller than 10 to the minus 5 times the thermal voltage. This figure shows the 5 lowest modes in each valley pair. Both of the gate and drain voltages are VDD. Since the G-directional length of the silicon channel is much smaller than Y-directional one, the 001 valley has the lowest mode energy. The DC input IV curve is shown in the left figure. The threshold voltage is about 0.23 volt. Also, the output IV curve is shown in the right figure. The on current is about 50 microampere. It is noted that the AC responses can be calculated only at discrete frequencies. Remember that following equations for the AC green functions, we need quantities at E and E plus half omega. Therefore, minimum non-zero frequency available in the AC NEGF simulation is determined by the energy spacing adopted in the DC NEGF simulation. For example, the energy spacing of 0.2 millielectron volt corresponds to about 48 GHz. For 0.2 THz, the energy spacing should be 0.83 millielectron volt. Therefore, in order to calculate the AC response at a very low frequency, a very fine energy grid should be introduced. However, at the low frequency limit, such restriction can be relaxed. AC self-energies can be approximated as energy derivatives of the DC self-energies. Moreover, the AC green functions can be easily evaluated with the AC self-energies and the DC green functions. Now, let me test our implementation at the low frequency limit. The admittance Y sub dG must converge to the transconductance. Also, YDD should be an inverse of the output resistance. In the left figure, the transconductance of the nanosheet transistor is shown. It is calculated from the AC NEGF simulation. The quasi-static result obtained from the finite difference is also shown for comparison. In the right figure, the output resistance is shown. It is the inverse of YDD calculated from the AC NEGF simulation. Again, it is compared with the quasi-static result. Good agreement is obtained for both cases. Such good agreement of the terminal quantities is not accidental. The electron density integrated over the YZ plane also exhibits good agreement as shown in the figure. The red curve is for the gate excitation and the black one for the drain. As the second example, the AC responses at non-zero frequencies are calculated. At non-zero frequencies, the wideband limit approximation is used for context only because it greatly simplifies the implementation. In this preliminary report, a simplified problem is introduced to reduce the computational burden. The DC output IV curve is shown in the right figure. The AC total current is obtained by summing the particle current and the displacement current. The gate admittance YGG is shown. Both of the gate and drain voltages are zero. As discussed before, the minimum non-zero frequency is limited to 48 GHz in this example simply because the energy spacing is 0.2 millielectron volt. Imaginary part related with the gate capacitance linearly increase with the frequency. Also, YDG is calculated. Its real part rapidly decreases at high frequencies. On the other hand, the imaginary part increased with the frequency. The real and imaginary part have the same amplitude at around 150 GHz. Let me conclude my talk. Up to now, the AC NEGF simulation approach has been demonstrated for nanosheet MOSFETs. At the low frequency limit, the AC NEGF simulation result have been compared with the quasi-static result. AC terminal currents at non-zero frequencies have been evaluated under the wideband limit approximation. As a future work, the present implementation will be extended to more general cases beyond the wideband limit. Additionally, the proof of the current conservation under the conventional simulation setup would be an interesting future research topic. This is Acknowledgement. Thank you for your attention.